Welcome back to The Explainer. Today, we're taking a look at a really fascinating data serialization format called Hf-Json 2.0. Now, right off the bat, I just want to set some expectations here. This isn't some flashy, disruptive tech that's trying to replace standard JSON across the entire web. Absolutely not. Instead, you should really think of Hf-Json 2.0 as a highly specialized, practical tool. It was designed to solve one very specific problem, and that is data fidelity. So if you've ever dealt with complex data types and worried about losing precision during a transfer, well, this explainer is going to be incredibly useful for you.
So that brings us to a fundamental question. Does standard JSON actually have an integer problem? Well, think of standard JSON kind of like your everyday household toolbox. You've got your hammer, your screwdriver, a wrench, and it's fantastic for like 99% of household tasks. It's simple, flexible, and pretty much everyone understands how to use it. But what happens if you suddenly need to, say, rebuild a high-performance engine? That household toolbox? Yeah, it's just not going to cut it anymore. You need a specialized mechanics toolkit. And that is exactly what Hf-Json 2.0 is for, data serialization. Because, as we're going to see, when you're dealing with extremely precise numbers, standard JSON is secretly hiding a limitation that can absolutely wreck your specialized data. Okay, so let's dive right into this. Section 1, the trouble with JSON. It really all comes down to how standard JSON handles numbers under the hood. We usually assume that if we type an integer, it's just treated as 1, right? But JSON is actually based on JavaScript's type system, which means it deceptively treats all numbers as 64-bit floating point numbers, or float64. Sure, it allows you to write integer literals, but if you try to pass a massive, highly specific number, like a 64-bit cryptographic integer, for instance, standard JSON can just silently lose that exact type fidelity. If you store a 16-bit unsigned integer, the receiver is just going to see a generic number. This perfectly illustrates why Hf-Json 2.0 is such a game changer for this specific problem. It uses strict string encoding with very specific prefixes, and it even slaps a CRC16 checksum at the very end. So our specialized alternative perfectly preserves exactly what type of number was sent, with zero guesswork.
Which leads us to Section 2, answer Hf-Json 2.0.
To fix this fidelity issue, developers essentially took a strict format that was originally built for a language called merge-e, and they decoupled it to make it completely independent. Now, every Hf-Json 2.0 document uses a really strict envelope structure. With standard JSON, you can kind of just throw an object or an array at the top level and call it a day. But Hf-Json 2.0, it requires exactly 3 top-level keys. No more, no less. First up, you have the Hf-Json key, which acts as the main fingerprint and holds your actual body data. Second, there's the version key, telling the parser exactly which spec to use, and right now we're looking at version 2.0. And third, the constraints key. Now, this last one is incredibly powerful. It literally promises the exact limits of the types used inside the document. This means systems instantly know if they can even process the file before they waste any resources parsing all that heavy data.
Moving right along to Section 3, 3 ways to structure. So a really crucial point here is how this format handles the actual shape of your data once you get past that protective envelope. Hf-Json 2.0 doesn't just let you build messy free-for-all data shapes, it actually gives you 3 distinct purpose-built structures. Let's demystify these real quick, because they are super practical. Your first option is rows. This is your standard row-oriented data. Very simple, highly readable, and perfectly fine for standard REST APIs. But it is a bit inefficient because you're duplicating field names and type info on every single row. So if you've got massive amounts of tabular data, you're going to want the second option, which is calls. This is column-oriented. You declare the field name and the type exactly once, and then just provide a single list of all the values. It is vastly more efficient for those heavy, data-intensive workflows. And finally, we have the DAG, or Directed Acyclic Graph. Simply put, this is just a tree-like structure that lets you use named links and references. If your data isn't just a flat table, but more like a complex web of interconnected pieces, the DAG structure keeps the whole shebang perfectly organized.
Next up is Section 4, a richer type system. Okay, we've talked about how Hf-Json 2.0 structures its documents, but the real magic is what actually goes inside those structures. Unlike standard JSON, which just kind of hands you a generic number type, Hf-Json 2.0 gives you a massive toolkit of specific atomic and composite scalars. Remember that mechanics toolkit analogy? This is exactly where it shines. You get whole for strictly unsigned integers, and int for signed integers. But it goes way further than that. You can express exact fractions using rational.
You've got floating points specifically labeled as LF real, which actually stands for low fidelity real numbers, kind of acting as a constant reminder to the developer that floating points are just approximations. It even supports complex numbers right out of the box. Things like Gaussian for integer complex numbers, or rational for rational complex numbers. The point is, you are never left guessing what type of math the original author intended. It's explicitly stated right there in the data. And it builds up to some pretty advanced concepts, too. The format totally goes beyond simple scalars. It fully supports quantities with actual units of measurement attached. We're talking SI units for temperature, or even Planck units for physics. So a value isn't just a random 300, it's explicitly 300 Kelvin. And then we get to what the source material playfully calls the final boss of Hf-Json values, the tensor. Now, in this context, a tensor is just a plain language way of saying a complex, multidimensional value. Let's say you need to transmit a 3x3 matrix of 128-bit complex numbers. Hf-Json 2.0 handles that cleanly, while defining the shape, the base elemental type, and the mathematical frame, meaning the specific mathematical rules or coordinate system it exists within. We are talking about absolute precision, fully serialized. All right, let's head into Section 5, Ecosystems and Eco-Files. Having all these rich data types is awesome, sure, but it does create a new problem. What if the receiving program just doesn't support them? Because as we know, different programming languages have drastically different capabilities. Python handles numbers way differently than C++, for example. So Hf-Json 2.0 uses these things called eco-files as a built-in safety net. Here's how it works. First, every language parser provides an eco-file that explicitly outlines its strict type limits. Then, the system gathers and consolidates all these eco-files from all the different languages operating in your ecosystem. Finally, the infrastructure uses these files as a sort of digital handshake. It calculates the maximum safe overlap between all the systems and then restricts data exchange to only what everyone can understand safely. It's honestly a brilliant way to make sure your data isn't accidentally corrupted when moving across a diverse tech stack. Let's look at a really practical example of this safety net in action. Imagine language A is the sender. It encodes a massive cryptographic integer, perfectly serialized just because its own ECO file allows for huge numbers. But then you have language B, the receiver, which is built on a much stricter framework. Let's say its ECO file maxes out at 128-bit integers. Well, thanks to that constraints field we talked about in the envelope structure earlier, language B doesn't even attempt to parse that massive number only to silently truncate it or crash. Nope. It just looks at the envelope, compares it to its ECO file, and immediately rejects the file safely. This guarantees that your data is never quietly mangled or mistranslated. It's binary. It either transfers with 100% fidelity or it fails safely. And that brings us to our final takeaway today. Remember, Hf-Json 2.0 is absolutely not trying to take over the world. If you're just sending a simple username and a status code between a basic front end and a back end, stick with standard JSON. It's still your best friend. But if you're working in environments that demand absolute mathematical precision, we're talking cryptography, scientific computing, or complex distributed systems where losing type fidelity is literally a catastrophic failure, then the specialized toolkit is exactly what you need. So take a hard look at your own workflows. Could your data ecosystem genuinely benefit from strict type safety? Thanks so much for joining me on this explainer, and I'll catch you on the next one.